Hello, and welcome back to Learning with Lee. In today's episode, we're going to take a look at low-level file I/O and binary file I/O in C. For this, we're going to continue to use polyhedrons and the parse polyhedron function that we discussed in the previous episode, so that we can basically read in a known polyhedron, in this case here from this file, and then we're going to end up creating a binary file to store a binary version of that polyhedron in. We're going to read that in after that, and check that we went through that entire process without any problems by outputting it using cout. So with this, we're going to end up using fwrite and fread. We'll get into fread in a little bit. To begin with fwrite, you can see that it ends up taking in 4 different arguments. You can see it either up where I have it described or down in here, where you can see the actual arguments and their names for it. So the first one is void pointer data. And it's important to remember that void pointer is just a pointer to somewhere in memory, just as an address. It doesn't have some of the information that we normally get with a pointer, because usually if you have a pointer to an int, it ends up having information about how wide and how large an int is, so that you can go forward one spot in memory. And that happens to be fairly useful for dealing with things such as an array of integers, so as you can rapidly go through it and know that if I want to do something like my current position plus 15, I know what plus 15 actually means, because it doesn't necessarily mean 15 bytes. Whereas with a void pointer, you know nothing about the information in there. You just have some set of bytes, some set of bits that you have in there. Then you have a size and a count. And while these aren't really as important for our current example, here's the major distinction between the two of those. If I had, say for example, that array of integers, and I want to store it into a file, well, I could just pass in for my pointer here a pointer to that array. So even if it just was like int, well, let's just write it here, something like int I, and it has 15 elements in it. Well, in order to do that in here, I could just write in I. And then what I could do within here would be something like size of int. Then over here, because this is the count, that would be 15, because I have 15 elements in there that are the size of an integer. And finally, I give it the file, and by file I mean file pointer, that I want it to write to. So that's all that you have to do for fwrite. It's fairly simple, but the major cost tends to be in setting up this buffer, in terms of setting this up correctly. But otherwise it's very efficient, very rapid, and it works at a low level, and it works for both binary, and technically if you want to, you could do it with text, provided that what's within your buffer happens to be characters, or things that can be intelligently converted into characters from binary. So that happens to be the value of fwrite. It technically isn't the lowest level of reading and writing functions. However, for those, you need to end up doing system calls, and those depend on what operating system you're using, such as in Unix, which is what Macintosh is based on. Linux is somewhat based off of it, but it's also based off of BSD and a few other sources. But for those, what you end up using is you end up using the create, open, close, read, and write functions, and those all happen to be provided for you by your operating system. However, those system calls are operating system specific, so they do vary between Unix, Linux, as well as also Windows. So it isn't particularly useful at this time for me to get into that specific level of detail, especially because the header files that each of these ends up being used in ends up being different, such as for this right now what we're using C standard IO, cstdio. And that is basically where you're going to find all these things for fopen, fwrite, and the like within C. And that's going to be the case regardless of whether you're on Windows or whether you're on a Macintosh or whether you happen to be using Red Hat. So that happens to be why it's nice to end up using this, is that this ends up abstracting you from the specific operating system implementation, and your operating system implementation is designed to abstract you and hide the fact of how the hardware implementation is from you. So that sort of is some of the different layering to it, but that's fwrite, and the real complexity comes in terms of creating this buffer. And that's what we'll get into right now. And whenever you're creating some sort of file like this, you're effectively creating a file specification. Think about all the different image types that are out there, whether you end up looking at a GIF, a JPEG, TIFF, whether you happen to be looking at a PNG, or any other type that's out there. each one of those has a very specific way that the data is stored within that file. That's what gives it a particular file specification. So whenever you end up deciding to store something in a file, you want to decide on a file specification so as that you can end up knowing how to read and write that information. So the first thing we're going to look at is this determine buffer size function. And that's because it not only happens to be used to determine how much data we're going to be writing and how much large of a buffer we need to write that information, it's going to tell us about how we're going to end up storing this in our file. To a certain extent. Technically, if we wanted to, we could end up using determine buffer size, and if we skip down here, we could do this addition in basically any order that we wanted to. It doesn't have to match up with the order that we're actually storing the data in, but it makes a lot more sense if it is in that same order. So the first thing that we need to consider is that we're going to want to store the size of the file, so that when we read that file, we can create a size of that buffer. And while you can end up getting that via system calls from your operating system, however, for now we're just going to store it in there so as we don't have to do something that is operating system specific. It happens to be a little bit of extra work in terms of having that extra bit of memory in there. Then we also need something in order to store the number of vertices that our polyhedron has. And realistically with this one here, similar to this example here, in case we want to store multiple polyhedrons, we'd also have to then store the number of polyhedrons within that file. And then for each of those polyhedrons, we'd have to store basically this set of data, which is just the number of vertices, because we need an integer for that, or more accurately, we need a size underscore t for that. Then we end up needing 3 doubles for each of the vertices for its x, y, and z values. Then we need another size underscore t in order to store the number of facets. And then we need to go through each of our facets because each one of these can end up having their own custom size for them because of the fact that their number of points varies. So for each one of their points, we need a uint. So we need to multiply the number of points by the size of a uint, or unsigned int. And then we also need to add in this size, which is the size of size underscore t, so as that we can also store the number of vertices on that facet. And that's really all that we need to store for it. So when we scroll on up to here for creating the buffer, now that we have how large it needs to be, and there is a minor thing of that, technically one of those things, and we'll get into that when we end up getting to the read polyhedron binary, the first portion of it doesn't really matter because we already are going to be reading in that initial size, but for output we do want this full buffer. So then we're going to allocate it, and malloc does return a void pointer because once again malloc doesn't care about what's at that location. All this says is that, hey, you have this block of memory starting at this address. So we have our pointer to that. We check that we actually successfully did it. If we fail, what we're going to end up returning, because this ends up returning a void pointer, is that our buffer will be null, so it'll return null from this, so we know if we end up hitting a fail state. It's not the cleanest or best way because we don't get a bunch of information about it, but in C, you don't have access to exceptions, so that's something that you really have to wait on until you hit C++, which is what we'll be beginning in the next episode. So for this one, what we end up doing is once we have this here, we then want to actually convert our buffer into a different type of buffer. And the reason for that is that otherwise, when we want to advance in that buffer, I can't just, for example, if I try to do something such as, let's say, buffer plus equals size of size underscore t, if I do this and then I try to build it, what you're going to see is it's going to give us this unknown size error. And that's because, as I was saying, void pointers lack some of that sizing information you get with all these other types of pointers. So any spot where you see me doing this plus plus to the size buffer, or in any way modifying the size buffer, I would actually be having to instead convert the size buffer into some other type, such as a size t buffer, and add that amount on. As well as I couldn't just do this direct assignment like I'm doing presently, I would have to end up using something such as memcopy in order to actually move the memory over from one location into the buffer itself. So that happens to be a bit of a limitation in terms of what you can do with void pointers, but it isn't too difficult to overcome it, and having to end up converting whatever type of pointer we're dealing with to whatever type we're going to be dealing with next, because you can see down here, we're going to eventually be converting it to a double pointer, and eventually to an unsigned int pointer also, depending on which thing we happen to be writing out. So we're going to output the size of our buffer, and then the number of points, because those are the first two things that we had mentioned earlier that we are actually storing in here. Then we need to store each of the vertices, so we convert it to a double pointer, so as that when we advance one spot in memory, when we do this plus plus, we move forward the size of a single double, not the size of a size t. As well as also it helps to ensure that everything gets stored correctly, allows us to do these assignments correctly, and one of the nice things that we can end up using, the subscript notation to actually write stuff out using this. As well as we can then do plus equals 3, for example, to move us forward 3 spots. And that's going to be slightly more efficient than if I had done plus plus 3 times in here, but not necessarily too much more efficient because it has to do some of the same logic when we end up doing this subscript 1. But the major thing is that for this we're using iterators to go through our list of points. We're going through every single one of them, and then we end up getting it out here. And what this is this is just me caching whatever our points.end is, so as I don't basically each iteration through have to go through and find the result of this series of functions where it ends up getting the points, then gets the end of it. And otherwise, it might not necessarily cache that for you automatically by your compiler. Some compilers might, but for this particular style of case here, that could actually give us problems in other situations where we're modifying the thing that we're actually iterating over. So then, once we have those written out and we have all of our different vertices written, we now output our facets. So we need to output the number of facets, so once again we need to convert our buffer back to size style buffering. And one of the important things is that each one of these I end up reusing the same names for these throughout here. So if I use double buffer later on, which in this case I actually don't, but because I'm using size buffer down here and size buffer up here, I do have to remember to assign this to this spot here in memory where the double buffer now is, because otherwise it'll just be where it was previously before I had actually done any of this, and it'll just start overwriting that information, and I'll wind up with a whole bunch of zeros afterwards, and it'll just fail and be completely messed up and give me incorrect data when I try to read it in. So once we have this all written out for the size of, well, the number of facets, what we then have to do is we have to write each of those facets to the buffer. So the first thing we're doing it with that is writing the number of vertices used by that facet, which, as I said, was just a size t chunk of memory, so we can continue to use our size buffer for this, output it this way, but we also then create this uint buffer. And what the uint buffer is it just is the size buffer as an unsigned int. And we use that to then write out every single one of those points since they're indices, and we then end up writing them to here. Technically, if I want to, I could use size underscore t for this, and probably should have done that originally, but then I'd have to go back, change polyhedron, how it happens to be done, change polygon, as well as also then some of the stuff we've done before for input and output, for it to then use size underscore t rather than just unsigned int. So for now, that happens to be good enough for understanding that, is that within here we're just going, okay, give me whatever index is at point sub I, and then store it in uint buffer, but the important thing to remember is I have to dereference it, because otherwise I'm assigning whatever this value is to a pointer, and all of a sudden I've lost where I was in my buffer, and I might be accessing memory I shouldn't have access to. Then the final thing I need to do is I need to update my size buffer's position, because I'm going to be using the size buffer first in this for loop during my next time through. So I need to make certain that it is where the uint buffer currently is. And that's really all you have to do for going through and writing out a binary buffer, and then you can just use fwrite on that buffer to write it out to your file. So that is writing a file in binary. Now we're going to quickly go over reading in a file in binary. I understand that some of this might be a bit quick, but I would recommend going back through this on your own. I will post the source code in the comments, and I would recommend using it and going back through and making certain that you understand the way that this works in here. So for this, what we have is we have a couple different things. We have create polyhedron and read polyhedron binary. And read polyhedron binary corresponds to write polyhedron binary, and then we're just going to take in a file name and we're going to get back a polyhedron pointer. So we're going to start off with it null, so as in case we fail, we end up being able to check that what we get back is null. However, if we don't, end up failing to open up the file, and once again, we use B here to represent that it's a binary file that we're reading in. Then what we need to do is we need to figure out how much of a buffer do we need? How much memory do we need? So the first thing we're going to do is we have this size t for buffer size here. We're going to be reading into that buffer size the very first size t bits, or really size t bytes, because size of returns the number of bytes in something. But we're getting back the number of size t bytes in there, and we're going to store that into this buffer size. So as we can figure out how large our file is, and how large our buffer resultingly should be. We create our buffer, as we did above, and then we use fread. And fread is basically the exact same as fwrite, just that you're reading data as opposed to writing data. So we end up taking our buffer that we end up writing into, and it should be large enough to end up holding our data. We care about our size and our count. So in this case here, we just are taking in our buffer size, and we're doing this once. It isn't like there happen to be multiple different things, and my example earlier can still end up working in case we want to do like size of int and then however many items are in an array. And then we actually are going to create a polyhedron from the information that has now been loaded into our buffer. And eventually then we're going to free it. So let's take a look at now we're reading it in. And this is just going to basically be the same as how we were writing it out, just in the opposite order. So we end up having a couple of pointers to buffers similar to what we did before. We have our size buffer here. One of the somewhat major things about it is that, in case we actually scooch back up here and take a look at it, is that our buffer size, we end up subtracting size or size of t from it, because we've already stored the first size t elements in this item here. So we don't need to copy that again into our buffer. That would just be redundant. As well as also then we'd have to do an fseek in order to skip back to the beginning to get that information again, because fread has already moved us forward this many bytes. So we're start off by looking at the number of vertices. We're going to then deal with our double buffer. This is just called double buffer because it's a buffer of doubles, not because it happens to be traditionally what is referred to by the term double buffer. So within here, since we already know the number of vertices, since we can just assign from the size buffer, and that's one of the nice things about having these as pointers here, is I can just dereference it and store that in some variable. And I can just do that real quick, store that here. One of the things that you'll note here is that I am plussing the size buffer, and then I'm casting it to a double pointer. And that's so as it moves forward size t chunks in memory. It's slightly more compressed in terms of here in how I've written it, though realistically I should probably just take this portion here and put it up here, but that'd be the cleaner way to do it. That'd be the more recommended way to do it, but you'll see code like this out in the wild, and you'll see much uglier code like this out in the wild, so it's good for you to get used to seeing some of that weirdness. Then within here, we read in, we create a vector for basically each one of our vertices. We read in its x, y, and z values from our buffer, advance our point in the buffer, add the new vector we've created to our polyhedron's points list, and then we advance through that for loop again. Once we're done with that for loop, we can now move on to our facets. Then in there, we end up determining how many of them we end up getting, which is why we end up using it as a size buffer, dereference it and advance it one. And technically, you could even do stuff in terms of using that, but that would end up being a bit ugly in terms of making certain that you end up having the order of operations correct for having the plus after size buffer with the dereference operator there also. Then, down in here, we're just going to go through each facet, create the different objects for those facets. Within those, we then need to basically figure out how many vertices they have, which is why we leave this alone as a size buffer for now. Convert to a uint buffer, since that's what each of those vertices is. Push those to the back of the points collection within our brand new facet. Then, once we're done with adding all those vertices to the facet, add that facet to the polyhedron, and advance our size buffer as well as, well, we're already doing the advancing here. So update our size buffer to point to the uint buffer because that's what we're using initially right up here. And then we return the polyhedron. And as you can see from running it, and I'm only going to go over this briefly, you can see from like this one here, which is 2457 and then 0136, if we look over here, you can see that these final two match up, and as I scroll up through here, you'll be able to see that they correspond to each other correctly, as well as for the vectors. And then up here is the original one, and in case I want to, I can compare those side by side, but I'll leave that for you guys to do on your own. So thank you very much for watching. I hope you've enjoyed learning about C and how you do file I/O and just I/O in general in C. You might want to spend some time messing around with not only what we've covered in today's lecture, but some of the stuff we've covered previously, just so you can get a bit more comfortable with things like scanf, printf, and all the different functions that we've covered. But really, we're going to be moving on from this in the next episode. We're going to be moving on to how C++ does it, and why streams get used, how those end up being used to abstract some of the stuff that we've been doing over the past several episodes, and how it's a bit cleaner and easier to use. Thank you very much for watching. Have a wonderful day.